things, dealing with many things concurrently. When I work with children in schools, I get them to actually construct the icosahedra through what we call a net, like on cardboard. We get them to literally draw these triangular shapes on a two-dimensional piece of paper. Then they learn how to fold it up and glue it all together, and that gives them a better understanding of, say, these pentagonal faces. So this is called the great, here it's known as the great dodecahedron, but that shape up there on the top right is what we were just looking at, the fusion of icosahedra. I'd like to show you another diagram out in the galaxy which relates exactly to the dodeca and icosahedral interplay, and it's taken from a little book of coincidences by John Martineau. The cover that you can see here shows you the relationship of Venus as it travels around the Sun. It takes 8 years to create this pentacle shape. And on Venus time it's actually 13 years. And so here we have a pentacle which is 5, an 8 years journey, but 13 years on Venus. So those numbers 5, 8 and 13 are part of the Fibonacci sequence that we were talking about previously. It's quite interesting that when we look at the planets, they're also relating to each other exactly in the nature of these 5 platonic solids. There's a beautiful interplay between the dodecahedron made of 12 pentagons, and the icosahedron made of 20 equilateral triangles are the last 2 of the 5 perfect polyhedra. They form a dual pair as each creates the other from the centers of its faces. They appear in a bubble form suspended inside of Mars's spherical orbit. The dodecahedron magically produces Venus's orbit as the bubble within, while the icosahedron defines Earth's orbit through its bubble's center. When we have 20 small spheres within the larger sphere, we form a dodecahedron, and if we were to look at the space within those 20 bubbles, there's a sphere here, and this defines the orbit of Venus here. And if we look closely again down here with the icosahedron, the space within the icosahedron defines the path of Earth as it goes around the Sun. It's quite interesting that a mathematical sequence known as the Fibonacci sequence was the inspiration for an astronomer discovering a kind of a planet, but actually an asteroid. So in 1778, J. Bode put this theory out that the planets separated themselves from the Sun in the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13. So here's the order of the planets. From the Sun we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. And there seemed to be some anomaly point around here. This symbol here was an unknown. There was a big gap happening there, so it was kind of predictable that these increments going 1, 1, 2, 3, 5, there was a gap, and they realized that there had to be something there, and that inspired Giuseppe Piazzi in 1801 to realize that there was a major asteroid there, and it was called Ceres in the asteroid belt. It's here. So from the same book by John Martineau, we're looking at the relationship now of Jupiter to Earth, and it appears that precisely we can describe that the path of Jupiter relating to the path of the Earth as we go around the Sun is described by the nesting of 3 octahedrons. Here you can see the Star of David once, then there's a smaller Star of David, and there's even a smaller Star of David. That Star of David is symbolic of the octahedron. If we look at this diagram down here, if this sphere represents the path of Jupiter, we place one big octahedral crystal inside, then another and another. So when we've inscribed it 3 times, that sphere in the middle there is the Earth sphere. So the relationship of this circle to that circle represents Earth to Jupiter. Also taken from John Martineau's excellent book on the relationships of the planets, there's an incredible relationship of the planets, especially Mars, Saturn and Saturn-Neptune. There's a beautiful relationship of how these planets describe or invoke the famous relationship called pi. As you know, pi is a relationship of the circle to the diameter, which is 3.14. So let's have a look here on this diagram. You can see here's the Sun. As Mars is going around the Sun, that circumference, the length of that circle, if it's unrolled, is this distance from here to there. So, but this radius of this great circle is also the path of Saturn as it goes around the Sun. So that means the relationship between Mars and Saturn is an exact pi ratio. This is true sacred geometry displayed in the cosmos at its best. I can't think of a better example to show that this world of sacred geometry is not only on the outside as well as being on the inside, but it's reflected around us. There is another example of pi as well. Here's the Sun in the center. As Saturn travels around the Sun, which takes about 28 to 30 years, if that circle is unrolled into a line, it becomes the diameter of the pathway for Neptune as Neptune goes around. So here are 2 classic examples how sacred geometry is expressed in the dance of the heavenly spheres. So we've looked at the overall view of the 5 Platonic solids. We've also looked at each Platonic solid individually. The only one that we haven't covered at the moment was the cube. So the next series of slides are just to give you a bit more insight into the nature of cubic consciousness. So here's the spherical formations of the tetrahedron, octahedron and the cube. You can see here that the solution to 4 spheres packing economically is based on this pyramid formation, which is tetrahedron, and the 4 centers create the pyramid shape. But it's interesting when you look at it as a shadow here, the 3 scalloped curves, it's very similar to the shape of the clubs, which is one of the 4 suits of the normal playing cards that we're familiar with. This may not be the case, but this is partly what sacred geometry does, that it invites you to look into familiar shapes that we've assumed and just used all our lives, but we haven't really understood the derivation of this shape. Therefore, you could think that the diamond shape here is the suit of diamonds. We also have the suit of hearts, and the suit of hearts is also the shape of 2 golden mean spirals as they form together sideways like that. The 2 spirals coming together making the heart. Okay. Here's the octahedron where we've got 4 spheres there, 1 in the front and 1 in the back, and that makes octahedron. And here you can see the traditional shape of the cube. It's just for you to learn through pictures. That's all we're doing here. We're learning through pictures. The essence of these diagrams are that they are psychoactive. They're triggering higher consciousness by teaching us to remember that the role of sphere packing is one of the highest forms of education. And here's more pictures of the cube. First of all, we know that another puzzle is in 2 dimensions. If we have a circle, how many circles can fit exactly around the original central sphere? Well, the answer is 6. So we know in 2D it takes 6 circles, but if these were spheres, we learned before that 12 spheres pack around a central sphere. Here, if you squint your eyes a bit, you can see that the hex view also depicts a 3-dimensional cube. or we could say that this is the hex view of a cube, hex referring to six-sided. And when we see the cube, the smaller cube in the middle, inside of a bigger cube, that's the definition of fractality, when the small picture is part of the bigger picture. The cube within the cube. In some literature that I have read, we hear of the Lord of the Electron, and his name was Metatron. And the symbol of Metatron was this cube, which was the fourth dimensional cube, when we look at a cube within a cube. Here's another view of the cube, where we can see the Star of David clearly. And here's the Star of David within the Star of David. Three-dimensional cubes hinting at a fourth-dimensional reality. And here's quite an interesting picture of the hex view of the silicon chip that we're all familiar with in our technology. You can see that there are 6 distinct rays coming out from the center, and that there's a hexagon with a hexagon within a hexagon. The mathematics and geometry of this computer chip is so advanced, I don't believe that it's actually Earth-based. It's some greater intelligence has literally brought this down to us, because the intricacy is so deep and so fractal that I don't think it was a human that actually designed that. It is also important to have X-ray eyes and discern the shapes of three-dimensional shapes by actually viewing internally. It's kind of like a clairvoyant gift to be able to look inside of these shapes. And this is called The Cube of Motion by Walter Russell, who wrote this extraordinary book called The Universal One. It's out of print, but every page in this book was highly illustrated with this incredible internal viewing of the shapes that we're familiar with. Most people are also familiar with the idea that our height, our physical height from feet to head, is identical to the span of your outstretched arms. It's something you can measure for yourself. So literally that forms a square, which is really, if we turn around, we fit into a cube. So here's a person standing in a cube. The ideal height for the ceiling of your house would be a double cube, because it fits in the ratio of the golden mean. It's a √5 ratio, which is part of the formula for the golden mean, which is 1 plus √5 divided by 2 is the golden mean ratio. So the ancients knew that the mathematics of the double cube was very important to them, because it was part of the biometrics of the human body. So often when you look at an Egyptian altar, you'll see that a priest is standing in front of a double cube, one cube with another cube stacked upon it. So it's quite conducive to have a house with high ceilings where there's lots of space and energy you can move through. This diagram that we're looking at now is part of the Masonic knowledge, the secret hidden knowledge, that when we unfold the Christian cross, it reveals a star tetrahedron. If we were to fold up the cross, as you know, it would form the cube. We just looked at some diagrams of the Star of David. So here's the three-dimensional view of the Star of David. If we can think of it as a cube, and when we stack millions and millions of these cubes packing next to each other side by side, we end up with this exquisite diagram here of the silicon chip crystal. So if you can squint your eyes like here, you can see that there's 6 circles around that. It's like a Star of David, hexagon, but if you look closely it's a cube. You can start seeing cube, and if you look even around it, you'll see that there's cubes within cubes, but you're really essentially looking at this shape here, the star tetrahedron. So it's always important that when you see a two-dimensional diagram of an atomic structure, that you're really viewing it in terms of three-dimensional shapes. Here's an exquisite picture of Metatron's cube, the Lord of Creation, showing his personal or psychic emblem being the Star of David within the bigger Star of David, which is really cube within cube. We call that fourth dimensional in a sense. We're looking now at another 6-rayed diagram, which is also another atomic structure. This time we're looking at the pattern found in another crystal called beryl. It's specifically an X-ray diffraction pattern, but if you look closely at it, it has the appearance of being a cubic packing of crystals. You can squint your eyes and sort of see that there's really millions and millions of cubes nesting side by side in this cubic matrix. This X-ray diffraction pattern is similar to the diagram that was given to us by Rosalind Franklin, who first discovered DNA, and the credit was taken from her to Watson and Crick. But it was a diagram very similar to this that inspired the discovery of the double helix. I just gave some reference to the idea of a fourth dimensional cube. I'm going to show you some more diagrams on that, but let's look at what is there for a fourth dimensional triangle. Have you ever thought of, if a triangle is two-dimensional, the three-dimensional version is a tetrahedron. So what's a fourth dimensional triangle? If you look here on this diagram, we can start in one dimension. We can say a line is one-dimensional. And then a two-dimensional diagram would be like a triangle. And we understand that the three-dimensional form of this is the tetrahedron. So my understanding, and this may differ from teacher to teacher, but if I had in front of me 5 tetrahedrons, so here's one tetrahedron. Imagine I had 4 other tetrahedrons exactly like this, and I was able to glue them together. So now I glue one tetrahedron here, one there, one here and one below, and now so I've got 5 tetrahedrons, but they form one cluster. And if I was to look at that as a unit, I would end up with what we call a fourth dimensional tetrahedron or fourth dimensional triangle. It looks very similar to this bottom diagram here. And what's interesting about this fourth dimensional triangle is that if I was to shine a laser down on this model and look at the shadow of this fourth dimensional object, an incredible shape appears, and it's the pentacle. So the pentacle seems to be a basic universal shape that has lives in other dimensions. So it's quite an amazing discovery that the pentacle appears as the shadow of a fourth dimensional pyramid. To give you an experience how to view a fourth dimensional object, it means if we squint our eyes, we will be able to see 5 different tetrahedrons all in the one shape. So look at triangle ABC as a two-dimensional triangle. There's ABC. We're looking at this information here. We're going to understand that these 5 formations are all tetrahedrons. So ABCD means you look at ABC and connect all these 3 points to this point here, D. So if you can squint your eyes and see that it forms a tetrahedron, then you can sort of view that on a deeper level. You're learning how to access multi-dimensions through your own perception. So let's look at one more here. B, C, D, E. That means if I look at the triangle B, C, D, just look at this two-dimensional triangle and connect those 3 points now to any other point, say E. If you can connect this E to those other points, out will jump a three-dimensional tetrahedron. That's the concept anyway. Sometimes you need to practice that, but it's there in front of your eyes. What we have here is a magic hypercube, or it's a fourth dimensional cube. You can see the cube within the cube, but it's also relating to a magic square. So you can take the numbers of a magic square from 1 to 16, a 4x4 magic square all adds up to 34, but we can magically transpose all those numbers in 2D into a fourth dimensional shape where everything still adds up to the same number 34. So if I add up this top plane up here, 11 plus 2 plus 7 plus 14, that all adds up to 34. That's the top of the inner cube, and the top of the bigger cube is 8 and 13, 12 and 1, that's also 34. So this is a fourth dimensional structure and also a magic square. Another word for hypercube or fourth dimensional cube is tesseract. So that's a magic tesseract. Now if we could look at this cube and see many other cubes all in the one diagram, then we have an understanding how it is formed. So here's a cube down the bottom here, right? And if you can sort of take one shape and drag it through the diagram, you will start to get an understanding how here's one cube is really a nest of 8 cubes in this whole diagram here. We just looked at one cube, but really there's 8 other cubes in this one fourth dimensional cube. So if you squint your eyes again, you might be able to see that with a slight change of your perception, you can see cubes and cubes at different angles. That's a very naive demonstration of what a fourth dimensional cube is. And if you can understand 2D, 3D, 4D, perhaps it's a suggestion that we've got a means now how to understand 5D and 6th dimension, etc. A veritable Jacob's ladder of dimensions that we are able to access. So if you understand what a fourth dimensional tesseract is and can nest a few of them together side by side into another one unit, this would give you a clue as to what a fifth dimensional cube is. So this diagram here will show you many hypercubes, like fourth dimensional cubes, forming the fifth dimensional cube. Again, it's a diagram where you'd have to squint your eyes and sort of mindlessly gaze upon it so that the magic of the meaning can jump out at you. What we're looking at here is a one-dimensional object. It has one surface only. It has no inside or outside. If an ant was crawling through that hole, it would keep walking and walking forever around it. It's not actually an object that can be covered. This is another multi-dimensional object. If you look closely at this design, it has a special name. I'm sorry I forgot the name of it, but it's one of those diagrams that you'll see in great books on psychology as an illusion. But this is a multi-dimensional object that seems to have just one surface. There's no distinction between the inside or the outside, in a sense. So this shape that we just looked at is very similar to this fourth dimensional sphere called the tube torus donut, because there is no real inside or outside. The reason why we call this a fourth dimensional sphere is that we know that a circle is two-dimensional, a sphere is three-dimensional. So imagine if we have a sphere and we are able to have millions and millions of other spheres in one plane. So here's a slinky. We join the slinky, we make a donut shape. If you can imagine that each one of these rings or ribs is not a circle now but a sphere, and we had millions and millions of spheres in one axis or one plane, suddenly you would get what we call a hypersphere. So when we say hypersphere, we mean that this is a fourth dimensional sphere. So this would give you a clue to interpreting what a fifth dimensional sphere is. We've just spent all this time examining the nature of the 5 Platonic solids. The ancients also were aware of another family or subfamily of interesting shapes called the Archimedean solids. The definition of the Platonic solid was that for any shape, every face was the same. Like if we looked at a tetrahedron, every shape was the same. That means that at this vertex here of the tetrahedron, if that's a triangle, 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 we could say that there's 3 triangles that meet at any vertex, at any corner or vertices that I touch, it's always the same shape. So the code for a tetrahedron is 333. If I hold this one here, it's 333. So a cube would have a coding of 444 because at each vertex or corner there was 3 squares, which is 444. But this particular shape here that I'm holding is different, and this is an Archimedean solid. It's actually called a cube octahedron. The reason why it's different is because at any vertex point that I hold here, and if I count the shapes, I've got a triangle, square, so they're different polygons. So the coding for this is 3434. So any other vertex that I select, I look at it and I say, yep, it's 3434 uniform. So the Platonic solids are known as the 5 regular solids because all the polygons around the corners are all regular. So the definition of an Archimedean is that it is a semi-regular solid. Semi-regular being that they're not the same polygons. So around any point we could have pentagons or hexagons or decagons, 10-sided. We're not limited as to how many sides the polygons are. We're only limited to the fact that at any point it must be the same coding. Okay, so this particular shape here is the cube octahedron, which means that if I had the normal cube, imagine this was like a big piece of potato and I was slicing the 8 corners at their midpoint. So if I found the midpoints of all these edges and just sliced all the corners off, I would actually end up with this shape. In fact, most of the 13 Archimedean solids are all based on the truncations or the slicings of these primal shapes. Here's another one of the 13 Archimedean solids, and by definition it means that at any vertex point that I can touch, I can look around and I realise that there's a pentagon, hexagon and hexagon. So that means the coding is 566. So if I turn it around here and I look at it, I can see pentagon, hexagon, hexagon, so it's 566. And again, anywhere else I look at it and I say, yep, pent, hex, hex. So it's a uniform in its apparent semi-regularity, and this again is a very familiar shape. Most people know this truncated icosahedron as a soccer ball, and we've been kicking around this shape all our lives and we didn't realise it was a truncated icosahedron. We've talked several times throughout this lecture about the cube octahedron, not realising that the cube octahedron was a result of the 12 spheres that pack around a central sphere. So here's a naive diagram that shows that around a central sphere we can have 6 spheres in one plane, or 6 circles. So and here's the nesting of or here's the kissing of the 12 spheres. And we take the 12 centres of the spheres and we end up with this masculine diagram. The feminine and the masculine. This diagram is taken from Buckminster Fuller's amazing body of work, and he was obsessed in his whole lifetime about this one shape. The reason why he loved this shape of the 12 spheres around the one was that it was the only known shape in the universe that was very compressible. I'm going to show you a geometrical model that shows the vector equilibrium, which is determined by the centres of these 12 spheres. So this shape here that you're looking at looks quite stable, but it's actually quite flexible as well, and it's actually the key to alchemy. The ability for shapes like lead to turn into gold was based on the ability of certain primal shapes to create other shapes like magic. What we are now looking at is the cube octahedron. These are the 12 centres of the 12 spheres. And we have rubber joins on the end of these coloured sticks here, which means here's a triangle and I'm holding an opposite triangle here. And if I fully compress this shape, or if I push towards, if I push my hands together, this whole shape just collapses into an octahedron. So here's an Archimedean shape that's become one of the 5 Platonic solids. So I let go and it compresses back. If I do a half a compression, just go halfway, if I go halfway, it actually forms the icosahedron. So that's the full shape. If I press halfway, it's icosa, octahedron, and if I compress it again, we get the pyramids. We get the pyramid that we're familiar with, and if we compress again, we actually get the omni-stable tetrahedron, the basic building block of all the universe. And when we let go, it forms the jitterbug. So his name, Buckminster Fuller's name for this cube octahedron was actually the jitterbug, because